Okay, so thanks, Johanna, for coming to this conference. And it's a pleasure to have you here speaking about quantum modularity of three manifold invariants and higher depth extensions.
Thank you very much for the invitation. Now, well, like Nikita said before me, the fact that this conference was delayed also led to a bit of a change of plans, because if I had talked last year, I would have chosen one topic for this presentation. But in the meantime, I've also become very interested in something else in this quantum modularity project. So this is what I will tell you is based on an upcoming paper with Miranda Cheng, Davide Passara, and Gabriele Scroy at the University of Amsterdam, where we study these number theoretic properties of certain tree manifold invariants. So I should say it's a bit of a departure from the previous talks today, well, in some ways, in others not. And it was a talk that's really, it is targeted to a mixed audience. So there will be a part that's very physics. So if for people who don't know the background, it's more storytelling. And there is a part where it's more mathematical, and I get precise. So to start from the very beginning, I would say that in 2017, so based on a series of earlier works, I list here one, but there are many more. Sergei Gukov, Dupay, Pavel Putrov, and Kumrun Bafa claimed the existence of a new class of topological tree-manifold invariants that they called Z-hat, or also homological blocks, which are associated to closed three manifolds M3, and which furthermore come in families, so they carry a certain label, what I called here A. So to explain what these invariants are and ultimately where my work sits in relation to these, I want to provide some context. So here's the first part. The story behind them has two sides, one of which is this physical side. And here the place to start is with some three-dimensional supersymmetric quantum field theories, which can be realized within the M-theory context, where a 3D QFT can be associated to such three manifolds M3 by taking this three manifold as the compactifying space on which to wrap a stack of M5 branes. And then via what is known here as the 3D correspondence, there is a map between this QFT and a different 3D topological quantum field theory on the internal space on M3. So then from a physical point of view, this Z-hat invariant was defined as a supersymmetric index, so something that counts objects, which admits a Q-series expansion, so a Q-series, which has integer coefficients. And what this counts are BPS states in the spectrum of this 3D SQFT. Now, on the other side, in mathematics, one important question here in low-dimensional topology is the definition and categorification of topological invariants for closed tree manifolds. And this point was in fact part of the original motivation for defining the Z-hat invariants as these Q series with integer coefficients. Something which was done starting from other known topological invariants. Now, what emerged from this endeavor was that the Z-hat, these possess further interesting properties. So in the case where the 3D quantum field theory has rank 1 gauge group, these invariants have been related relatively recently, so in this paper in 2018, to certain modules for logarithmic vertex operator algebras. And they have furthermore been shown to have peculiar number theoretic properties. So they've turned out to be this quantum, what are known as quantum modular forms. So during the next maybe half an hour, I will elaborate on each of these points. But then one remark that I would like to make now is that this quantum modular structure of the homological blocks has also been shown to tie in nicely um, here with the resurgence analysis, where these guys are related to trans-series expansions of Z hat. So now the results that I've enumerated so far, these have been established for rank 1 3D SQFTs. And my work within this line of research has been looking at how this story extends to higher rank. And there are some clear expectations with regard to this generalization. For example, the log VOA characters should be replaced by their higher rank counterparts. And instead of quantum modular forms, here the higher depth versions that I've mentioned um, earlier, these should come into play. So then one may wonder, what is then the motivation for pursuing such a generalization if a priori it might seem straightforward? Well, the point is that the number theoretical properties of these invariants, once they are established, they are rather powerful. And in the same way that geometric tools can be used to gain physical insight in certain contexts, and we will hear about this, for example, in one of the other lines of research that is close to my heart in connection to tau functions and topological strings. So this will be tomorrow and Friday, and the talks that Jörg will give. Well, here as well, the problem can be turned around, and the quantum modular structure can be leveraged in order to deduce the Z hat invariants, so these homological blocks or manifold invariants, in cases where their calculation from the physics side may not be available. So having sketched this as a broad overview, I will now go through each of these points to actually review how these invariants are defined. And at rank 1, what their relation is to log VOA characters and to quantum modular forms, also giving more background in each of these areas. And afterwards, I will show what new features emerge from what I have been doing at higher rank. So to set the stage, the three manifold invariants that Z hat have been defined in the context, like I said, of the 3D correspondence. For certain three-dimensional supersymmetric gauge theories that can be realized within M theory as follows. So the space-time background is a product of the time direction, a Calabi-Yau threefold, and a 4D Tau-Knot space into which the three-manifold M3, that is this one, and a disk are embedded as special Lagrangian submanifolds. And then taking a stack of N5 branes and wrapping them on this space, the theory which lives on this stack of M5 branes is the six-dimensional 2,0 superconformal field theory with Lie algebra G, which will be of A-type. And then there are two avenues to take. On one side, reducing this theory on the internal three-manifold creates an effective 3D and equal to two supersymmetric gauge theory, which with gauge group whose Lie algebra is this G. And this theory depends both on the internal three-manifold on M3 and on a choice of boundary condition here for the two-dimensional boundary of the 3D spacetime background. And then moving to the other side of the correspondence here lies the 3D QFT that lives on M3. And this is three-dimensional Chern-Simons theory with complex gauge group. And there is a correspondence here between the boundary conditions for the space-time 3D theory, T of M3, and abelian flat connections on the Chern-Simons side. So then starting on this side of the correspondence with 3D Chern-Simons theory, the z-hat invariant here was defined through its relation to another well-known invariant of three manifolds. So this is the Witten-Reshetikhin-Turaev invariant of the M3, which up to some normalization can be identified with this, so the partition function of 3D Chern-Simons theory on this manifold at a certain level K. So this is given just in terms of the Chern-Simons tree form. Now we're deriving this relation between the two invariants. The aim was to define this homological block from the WRT invariants as a Q series, as a convergent power series in a parameter Q with integer powers and integer coefficients. When this expansion parameter lies inside of the unit circle, or equivalently given its definition in terms of the modular parameter tau, when tau takes values on the upper half plane. So more precisely, the starting point was to look at a certain type of three manifolds whose corresponding WRT invariants could be analytically continued away from Q at roots of unity. And the idea was to rewrite these invariants as a linear combination of the z-hat, which had these properties to be Q series with integer coefficients and so on. So what this linear combination in the relation is, so up to some factor, this relation includes a summation over connected components on the moduli space of abelian flat connections on the stream manifold M3 of the exponentiated Chern-Simons action. And this is multiplied by a Fourier summation of the perturbative 1 over K expansion related to this K of the WRT invariant around the corresponding abelian flat connection. And in fact, there's a little bit more to this because here there's also this S, which is a matrix, and it is a transformation that effectively implements a change of basis. So there is a sequence of steps here, which led to this definition in the relatively simple rank 1 case where this 3D space-time symmetry quantum field theory has gauge group SU2. However, there is in principle no obstruction to the generalization of this definition to higher rank. And this was indeed already conjectured in the original paper by Gukov, Petrov, and Vafa. So the modifications are, what they did was appropriately modify some of these elements. So this prefactor, the summation set, and also this ace matrix is different. Now, on the other side of the 3D correspondence, now from the point of the space-time 3D SQFT, here this invariant was defined as a half index. So that means that this is supersymmetric index for the n equal to 2 supersymmetric gauge theory, when the space-time background is exactly this twisted product of the disk and a circle with certain prescribed boundary conditions. Now, in this case, the corresponding Hilbert space of VPS states is doubly graded, and the z-hat is equal to its graded Euler characteristic. So this definition is in terms of the dimensions of these Hilbert spaces, and is indeed a convergent Q series when this parameter Q lies inside of the unit circle. So now more motivation and background is to say that when this 3D theory T of M3 has a Lagrangian description, then this half index quantity, or what is essentially here, what this is a 3D, 2D coupled system between the bulk 3D theory and boundary 2D. So that in this particular cases, the half index can be computed by a method called supersymmetric localization. And in this case, schematically, the result is of this form. The integrand receives a contribution from the bulk 3D theory, and another contribution from the boundary 2D degrees of freedom that are coupled to this. And this is what is, it's essentially the elliptic genus. So, okay, for now, this is very schematic. Now, the point here is that in principle, it would be possible to glue two such disks together to create a two-sphere, and thereby relate the half index to the superconformal index of this 3D theory T of M3, when now the space-time background is the sphere cross a circle. And then it has been conjectured that this should be the case by that the super conformal index can be expressed in terms of products of this half index by summing over uh, the full set, by summing over the elements that label them. However, what you have here is actually the half index as it was defined, and what needs to be an appropriate extension of this guy when this parameter q lies outside of the unit circle. And here is one somewhat subtle point in that these objects must be somewhat more than just a simple analytic continuation. And this is, in fact, one important point which I would return later in the talk, where quantum modularity plays a role. So, okay. In the beginning of this talk, there are 2 points that I've mentioned. The relation, the definition as an index that counts BPS states. And I also mentioned the resurgence aspect. So the resurgence analysis of this invariant in its simple form dates back to some of the early work on their properties. So here, Z hat as a Q series. I said it's a Borel resummation of a perturbative series in 1 over K. And this in the radial limit, so this is this expression here, this can be related to the Z hat evaluated when the parameter is minus K. And the difference between them is just a perturbative series. Now, okay, what I've said here is not quite universally true in the sense that the specific statement is somewhat simplified and it only occurs in a certain class of examples. So at rank 1 and for a certain type of ciphered 3 manifolds entry. However, this is indicative of the number theoretic properties, specifically the quantum modularity properties of this invariant. So this is something that I will say more about when I actually discuss quantum modular forms. So for now, we can pause and put this to the side. But okay, doing this, we can zoom back out because so far I've given a bit of the physics overview for the background and definition of these invariants. However, now to be more precise, these guys were also given a mathematical definition in terms of the topology of the corresponding 3 manifold M3. And this, you remember, I did say in the beginning, this mathematical definition was given for a certain class of manifolds. So this is what they are. So they are plumbed 3 manifolds. And then this definition in terms of the WRT invariants that are much better studied was done starting from this class of 3 manifolds. So now to say what these guys are, plumbed 3 manifolds, they represent a subset of closed 3 manifolds that are defined starting from a plumbing graph, like I've drawn here. So this is a weighted graph, which is assumed to be connected with nodes in a set V, and they are joined by edges, which are in a set in a corresponding set E, where each node has an associated integer weight alpha. And then all of this data can be encoded in what is called the adjacency matrix M, where the weights appear here on the diagonal. And then for any two vertices that are connected by an edge, the corresponding entry in this matrix is equal to 1. Now, given this data, the plumbed three-manifold M3 is then obtained by dense surgery on the corresponding link of unknots inside of a tree-sphere. So to the plumbing graph, assuming that there are only 3 external nodes and 1 central node, there would correspond such a link of unknots. And then the 3-manifold is obtained by cutting out the tubular neighborhood around each of these rings. So, okay, this class of manifolds contains ciphered fibrations. And the example that I will discuss here that will be relevant, the 3 manifolds will be Briscoe spheres. So these are 3 manifolds. These are cipher manifolds with 3 singular fibers whose plumbing graphs are exactly given by stars that have 3 rays. And these 3 manifolds are also specified by a defining equation that here in terms of 3 relatively prime integers, P1, P2, and P3. Now, the only restriction that needs to be imposed here in order for this Z hat to be convergent to skew series is that the adjacency matrix M has to be weakly negative. And that means that it has to be negative definite when restricted to the subspace that corresponds to high valency vertices, which are those connected to 3 or more edges. So concretely, in the case of just the 3 star graphs, that means that this entry, the one corresponding to the central vertex, or in the M inverse matrix, this has to be negative. So now in terms of this topological data, the Z hat invariants were defined by an integral. So here I'm writing it at rank 1 for simplicity. So this is a contour integral, which contains, here would be the factor that contains the contribution from the bulk 3D theory. And there's an additional factor that encodes the contribution from a lattice theta function for this lattice that is determined by the adjacency matrix that enters here in determining the summation set. And here you may notice, if you recall, the structural similarity to the localization result that I flashed earlier, which is no coincidence. This was the driving idea that led to this mathematical definition in the first place, in trying to write something that matched the localization answer. So what this integral does is it picks up the constant terms with respect to this collection of integration variables Z, and it allows to write Z hat as a Q series. And here you might see why I was droning on and on about certain constraints on how to define this as a convergent series when this parameter Q is smaller than 1, which therefore would determine whether or not Z hat is geometrically well defined in this manner. And why does so this all hinges on this M3 being weakly negative, because then in integrating out terms, here M inverse would enter with the correct sign as a result of this. Now, when this is the case, like for example, in the M3 Briscoe sphere cases, then the Z hat invariant, so here for an example, has turned out to be a linear combination of these guys. So these are false theta functions that you can see defined here. So they are just Q series, but which have this extra sign factor, which is why they are called false. Without this, they would just be honest theta function. So, okay, having said this, I have to mention a somewhat technical point with view to the later on in the talk when I discuss the higher rank cases. So the structure of these homological blocks, what I've shown, so being proportional to combinations of false theta functions, this holds quite generally in the case of Risk-on spheres, where this indices, so if I may go back actually for a second. So the indices here of the theta functions, you see there are two integers, P and R. P denotes the rescaling of the lattice over which these parameters are summed. And R is the honest parameter that enters. So P is fixed, R changes. These indices, they are the R's, they are determined combinatorially in terms of the P1, P2, and P3, which determine the topological data. And these guys can be neatly packaged into a particular orbit of a Weyl representation of the modular group of SL2Z on a certain larger space of such false theta functions. So where the index R is allowed to run over a larger set, it runs modulo 2p. And then the orbit that is actually relevant here, this restricted guy, is something that is determined by a set of integers that again depend combinatorially on the topological data. So since this is a technical point, I will not elaborate further on it, how this is actually constructed. But I did want to at least mention it because I wanted to state that this organizing structure exists and it will have an interesting role to play in the more general case at higher rank. So, okay, that was the lightning review. I guess now is a good time to pause and see where we are, because we have seen in this physical overview the physical origin of the z-hat invariants, both from the perspective of the 3D SQFT and how this is formulated then in terms of the topological data for the three-manifold M3. So now we can turn to the relations on the mathematical side finally. First to the characters of logarithmic vertex operator algebra modules. And then more importantly so this part will be very quick. And then more importantly for my talk to their number theoretic properties. So the first point to say with log VOAs when introducing these in here is that they offer a controlled environment to study the representation theory of non-rational VOAs, and they underlie 2D logarithmic conformal field theories. So key features here are that the OPEs and the correlation functions, they can exhibit logarithmic behavior, and the algebra has reducible but indecomposable modules. Now, so here, a lot of this would just be a few notions of background. The only thing that we need are some results. And the two cases, those of the singlet 1, p algebra and the triplet 1, p algebra offer the simplest families of such log VOAs. So they are determined by this parameter p, which is the same as before. This is an integer. The central charge is defined in terms of this parameter through these combinations of square root of p and the inverse. And it also enters here in the definition of the energy momentum tensor and screening operators Q, which are defined in terms of this and then free boson field. Now, the triplet algebra is defined to be in the kernel of this screening operator Q minus, on the lattice VOA V, which is associated to a one-dimensional rescaled lattice, so rescaled with respect to the integers. On the other hand, the singlet algebra, this embeds into the triplet, and it is defined as the kernel of this screening charge on the Heisenberg algebra, which is defined by the modes of the scalar field. So all of this is background. If it's somehow familiar, fantastic. If not, it doesn't matter, because the only thing that we need from this with regards to the study of the z-hat invariants are the characters of certain modules of the triplet algebra, whose constant terms, what I denote here by just the z0, are characters of the singlet algebra that take the form of this type of Q series. And these are familiar, in fact, because staring at them, one notices that they are in fact proportional up to a factor of the Dedekind eta function. They are proportional to the false theta functions that appeared here in the rank 1 z-hat examples for Brieskorn spheres. And like I said, in general, in these cases, the z-hat invariants have been shown to be proportional precisely to linear combinations of these singlet characters. So there is this interesting relation that was discovered experimentally, empirically, between these homological invariants of free manifolds and these characters of logarithmic VOAs. So this was at rank 1. What happens at higher rank? In this case, there are more free bosons here. Their number is equal to the rank of the Lie algebra G. And the lattice A is no longer a 1D lattice. It is proportional to the root lattice of the algebra. And then the higher rank characters for the modules that I mentioned on the previous slide have been relatively recently computed. And the singlet algebra character that will be relevant for what I tell you in the higher rank story is proportional to this doubly graded Q series, which is specified by these two integer labels that in this particular example, I just set both to 1 for simplicity. Okay, so this wraps up the part on the log VOAs. I will come back to this point in greater depth when I actually come to discuss concretely the rank 2 z-hat invariants. For now, we can turn the page and look at their number theoretic properties for these Q series, which I said have turned out to be quantum modular forms. And I don't expect that these are familiar to people. So in order to define what these are, it will first be useful to review ordinary modular forms and some examples. So now to the fun part. So the modular forms are holomorphic functions defined on the upper half plane, on which the modular group acts transitively by a fractional linear transformation, like you see here. So then a modular form of weight W and with some multiplier system with respect to a subgroup of the modular group. For this, the modular transformation that I denote here by this slash operator, this is given by multiplication with a factor that depends both on gamma on this element and on the weight. And then the function f is a modular transformation, a modular form, if it is invariant under this modular transformation for all of these elements gamma. Now, familiar examples that have already come up are the lattice theta functions that are Q series defined in terms of this parameter Q that runs over the integers. And then particularly relevant for this discussion with regards to the homological blocks are the theta 0 and the what is called the unary theta functions that are defined for this rescaled lattice, where the sums over k are identified modulo 2p with an integer. In these two cases, the weights are a half and respectively 3/2. So now, the modular forms, they are defined on the upper half plane. But in this radial limit, where Q approaches unity, or equivalently, the modular parameter approaches a rational number, then the modular form defines a function on the rational numbers. And then quantum modular forms come in precisely to generalize this, being defined exactly on the boundary of the upper half plane. So now, the original definition that was given for these guys roughly 10 years ago by Don Zagier was that the quantum modular form of weight W and with a multiplier system with respect to a subgroup of SO2Z is a function that is defined on the rationals, like I said, such that for any gamma in this group, the corresponding function P that is given by the difference between the original function f and its modular transform has better analytic properties than f itself. So what this means is that this function p, which is a cocycle, encodes the obstruction to modularity of the function f. Now, better analytic properties is very vague, and it's on purpose very vague in order to accommodate for a wide range of examples. And in fact, these examples clearly include the modular forms because in this case, P simply vanishes. Now, a stronger requirement, something that's a bit more constraining, is in the definition of strong quantum modular forms. So a strong QMF is an object with a more stringent structure, which associates to each rational number a formal power series in a parameter T with a stronger requirements on its behavior under modular transformations. So with F defined on the union of infinitesimal neighborhoods of these points X, the function P, the cocycle, is defined by this identity, the difference between the original function and its modular transform, between countable collections of formal power series. So the point is that then this function admits a power series expansion in T, which is convergent in some disk of positive radius around the rational points X. And the earlier example that the earlier examples that I was giving, the Z hat invariants, and implicitly also the rank 1 log VOA characters, they all fall into this class of quantum modular forms. Now, in order to describe concretely these guys, so a bit more than this, to describe the quantum modular forms that are relevant here, I need to introduce the following integral formulation for them. So considering a modular form G of weight W.
Ioana, sorry, can I just ask you to go back one slide? Can you just highlight this property of being strong? What that implies in practice? I think I missed it.
It just means it defines a little bit better what this better analytic structure is, i.e. that these guys actually have a power series expansion in this T. So they're not really just defined on the rational numbers, but they have this power series expansion in a small deformation. So they are convergent power series in a small disk. So if we look here, it becomes a little bit more clear, visual, what this actually means. So let me just adjust. So a way to define quantum modular forms is given what I said here. So a modular form of a certain weight. It is possible to define its holomorphic and non-holomorphic Eichler integrals by integrating this guy with appropriate measure factors that depend on the weight in each case. And then the integral, okay, it's clear why in one case it's holomorphic and in the other case it's the non-holomorphic integral. Now, what this means is that for a modular form of either integer or half integer weight, which has a Fourier expansion in terms of some coefficients. So this could be 0 in some cases. This is just the generic form that we have seen as a Q series. The holomorphic Eichler integral is also a Q polynomial, and it has the same Fourier coefficients, but it also has an additional factor that depends on the weight. And okay, these examples in general are, these integrals are examples of quantum modular forms of weight 2 minus w, what appears in the exponent, because the difference between them and the corresponding modular transformations are period integrals. So this is what better analytic property means. And now to be even more precise, if you recall the rank 1 examples that I was mentioning for the Briscoe spheres, which were linear combinations. Oh, if I can see. Okay, on my screen it doesn't quite show. Okay. These were linear combinations of false theta functions. Well, the false theta functions are exactly the holomorphic Eichler integrals of the unary theta functions, which are modular forms. So they are, by definition, they fall into the quantum modular form category, and consequently so do the z-hat invariants. So now this was at rank 1. So the story, as I've said it so far, has been tailored to the rank 1 cases. But now, of course, my aim is to discuss the generalization of this. So what is the higher rank counterpart? What to expect for the number theoretic properties of these z-hats? Well, the higher the quantum modular forms that I mentioned at the beginning of my talk. So these guys are defined inductively with respect to the quantum modular forms of lower depth. So that means that similarly to your definition of the ordinary QMFs, which are depth 1, then in the depth n quantum modular form case, f is a function defined on the rational numbers again, but it's such that the difference between the original function and its modular transform is now required to only be sum of quantum modular forms of lower depth and possibly multiplied by some real analytic functions. So now examples which extend the Eichler integrals from the previous slide, and that will be relevant later, are these non-holomorphic iterated or nested Eichler integrals, whose integrand is a product of modular forms of weight W1 and respectively W2. Again, with the appropriate measure factors included here that depend on the weights. So no surprise, this is a depth 2 quantum modular form, and this is something that follows from the behavior under modular transformations. I will just leave this here. I will not go through it. I know that the slides are there, so we can come back to this, but it's technical. So skipping the fine print here, The main point is just that such iterated Eichler integrals are related to rank 2 homological blocks. So we come now full circle, and I will say why this is the case. So concretely, when this 3-manifold M3 is a Briscoe sphere, like in the previous examples, and the gauge group of the n equal to 2 supersymmetric QFT, the space-time theory, is SU3, then the z hat invariants have been shown to be proportional, forget about what this is, to a linear combination of characters here of the rank 2 singlet 1, p algebra. So these are, I will come back to this point. These are doubly graded Q series that carry 2 integer labels. That's what this S is. The S are bounded between 1 and P. And all of this depends on just on the topological data of the 3-manifold of the Briscoe sphere. So there is a relation between the S parameters and these integers, the PI. So now, in a few minutes, I will discuss how iterated Eichler integrals are actually derived from these Q series, which will also show implicitly that the Z hat are higher depth quantum modular forms. But before I get there, there is something else that needs to be said. There's a bit of a glaring elephant in the room. So now we come back to the roadmap. So while it is all very nice, certainly, to see expectations confirmed, that there's this relation between higher rank homological blocks and log VOI characters, and quantum modularity does extend naturally to the higher depth variant. It would be well justified to ask if there is some reason to investigate this beyond just pure curiosity. Is there something to gain from actually going through this process of figuring out the quantum modular structure? And indeed, this is the case, because otherwise I would not be talking to you about it. So you may recall at point 1, there's this expected relation between, okay, I wrote it very small here, between the half index and the superconformal index. That involves both of these guys, the Z hat and appropriate extensions when tau is in the lower half plane. But recall that this has to be more than an analytic continuation, and I will justify a little bit in a minute why it's not so obvious how to do this. But okay, the point is that there is a problem to solve here. And this is one instance where quantum modularity plays a role. Now, at the same time, one may look here at the second point. For other instances in physics where quantum modular forms and their higher depth counterparts have appeared, to try to find a similar behavior when working with the homological blocks. So are there some similar points? Okay, this is the next point to discuss, just a review of a different context where these guys have appeared. So if we turn now to topologically twisted n equal to 4 pure super Yang-Mills theory on, or also what is known as Vafa-Witten theory, on certain for the space-time background, certain compact 4 manifolds. Now, the partition functions in this context have been shown to display an error to modularity under an S transform. So this is a transform on the complexified gauge coupling. Originally, this was discussed quite a long time ago, so in 1994 by Vafa and Witten. However, modularity is thought to be more important than holomorphicity, and this can be restored. So the modular anomaly it turns out in these cases to be an integral of a modular form. So it has one of the defining properties of a quantum modular form. It's something that's what is known as a mock modular form. And this can be traded for a holomorphic anomaly by adding a non-holomorphic period integral to the partition function. So, okay, these are just words on the background to this. Now at higher rank, this generalizes in a similar way to the way the Eichler integrals were related to their iterated versions. So the modular anomaly includes a shift by iterated integrals of theta series. And this is a point that this is something that Jan Marschott has discussed in the past in his papers, and how these can be traded for a holomorphic anomaly in the higher rank. And then furthermore, this was found that the holomorphic anomaly, so the holomorphic derivative roughly of the partition function, satisfies a recursion relation that is schematically of this form. So it's a weighted sum over products of lower rank partition functions. And having this sort of relation that is satisfied constrains what form the partition functions can actually take. And then even more recently, so I can't see on the screen. Even more recently, last autumn, this problem was picked up again, and there was a physical explanation that has been proposed for it. So, okay, the original proposal already goes back to the Waffa-Whitlam paper in 1994, but more recently it was verified by examples where this anomalous non-holomorphicity comes from. But now seeing this sort of behavior, it would be well motivated to ask if, in the case of the homological blocks, since mathematically sort of the same structure appears, do the higher rank functions sort of know something of the lower rank ones? Okay, so with this in mind, I see I have maybe 7 minutes left. With this in mind, we can return to the z hat as defined mathematically for the weakly negative plumbed three manifolds. And with tau in the upper half plane, and see what can be said if we go to the lower half plane. So just naively speaking, if one looks at the 3D Chern-Simons theory, they're changing the sign of this level, K, is formally equivalent to changing the orientation on the three manifold. So naively, one could expect the same definition to hold, that going to the lower half plane, you just flip the orientation. But the requirement then for the mathematical definition to hold, to give convergent Q series for Q for Z when Q is both inside and outside of the unit circle, this cannot happen. It's incompatible with the actual expansion in terms of the actual integral definition. So the point to note is that what the requirement actually is that the companion function for the z hat in the lower half plane must be somehow different, while nevertheless agreeing with the homological block in the upper half plane in the asymptotic limit where tau goes to a rational number. So this is precisely where quantum modularity helps to find the companions. Okay, so now I come to what we see concretely at higher rank. If we just restrict for the simplicity's sake to rank 2 to make equations still manageable. And okay, I will be mostly talking about Briscoe spheres, but there are certain more general cases that still where we still see the exact same things. So I will first give the highlights, and then maybe in a couple of minutes, we can just concretely look at some more detail as well. Okay, so point 1, this is just a repeat of something I have already mentioned, that these Z hat invariants are linear combinations of the rank 2 singlet characters, at least in this with the particular restriction that I've mentioned, and for the particular three manifolds that we are considering. The companions, these guys in the lower half plane, these are the iterated non-holomorphic Eichler integrals. So they are depth 2 quantum modular forms. And the integrals here, they contain products of unary theta functions and of products between the unary theta function with the theta zero. And then the reason why I've mentioned that those orbits of Weyl representations of SO2Z, these guys turned out to actually have quite a beautiful combinatorial structure with respect to the topological data of the three manifold and also with respect to the modular group. So this is similar to the rank 1 case where the theta functions got organized into orbits of the Weyl representation, except at higher rank, the structure is much richer. So to say a few things, so I've written schematically here, just the homological block, and then the companion in the lower half plane will be in the span, so it will be linear combinations of these two blocks. So this is something that's more complicated. It's the non-holomorphic, that's what the star stands for, Eichler integral of something that is a linear combination of the theta, the unary theta and a theta zero, and this just has unary theta functions. So okay, the point with all of this is that among all of these guys here, we actually do indeed see the orbits of unary theta functions, these guys that appeared in the corresponding rank 1 homological blocks. So just looking at each type of manifold and doing this analysis. So, okay, I'm out of time. Luckily, this was intended. I have a few backup slides if anyone wants to actually see the fun calculations that one can do, the actual procedure of deriving these, starting from the so the doubly graded Q series. Of course, the more general one that actually has generic parameters here, not just 1 and 1, are needed. But how to then split these appropriately into what will be individually higher depth quantum modular forms, but of different weights. How to take the limit to when tau goes to a rational number, and then when it goes, what switching the signs, the sign of tau means in terms of these series. Actually writing these guys concretely, doing some work to rewrite them as non-holomorphic Eichler integrals in terms of product of theta series, finding the companions, and then writing the final result in the way that it actually appears, so not just schematic, but actually what these blocks are combinatorially. Okay. This was the point that I mentioned schematically, how the rank 1 orbit of the Weyl rep actually enters inside into one of these contributions. And now, I guess with 1 minute left, I can conclude. So the first 2 points are really just a summary of what I've said. The 3 main takeaways that at higher rank, these homological blocks, they are indeed still related to characters of this log VOA. The companions are non-holomorphic iterated Eichler integrals that we can calculate. They have a very nice combinatorial structure, which was actually amazing to see that from what seemed like a mess, there was beauty and magic. And yes, we do indeed see in a certain way that the higher rank case knows about the lower rank. And now this is just really scratching the surface of what can be done with this. So the motivation for doing this project in the first place is to use it as a tool to extract predictions when the physics isn't there to help yet, to explore links to the logarithmic vertex operator algebras, because so far it's really just empirical, it's experimental. It happens to be there, but without a clear explanation for why exactly, although some intuition exists. And ultimately, what can be said from the physics, knowing this quantum modular properties. That's it.
Thanks very much. Is there any question? Yeah, Andy?
So you might have already addressed this during your talk, in which case I'm sorry. But can you say just slightly more about how you know which log VOA occurs for a particular three-manifold in-flight connection?
Just experimentally. Like really, this is the case. There's no guiding principle. It's just looking at the log VOAs that have been computed. Okay. So there's only ever the singlet 1, P algebra. Like that's it. Either lower rank or higher rank. And the actual characters that appear are what they're called atypical characters. So it was just an observation in the very beginning, just looking at this z hat invariants and just comparing with characters that this correspondence was just spotted, and then try it for more manifolds, which means changing these indices that were labeling the characters. And yeah.
I see, but you're saying, I mean, it sounds like there's literally some operators that live on the boundary, right, that make that VOA, but you're saying that no one has kind of constructed those operators.
And I'm not quite saying that. There was work by Gaiotto and I don't remember the other authors, I think Di Mofte. They were looking exactly at 3D theories twisted and at operators that live on the boundary, but that's recent. That's from last year, last autumn, I think. But there's no direct understanding yet.
I got it. And then maybe one other little thing in the SU2 version, if I understood right, it was just abelian connections that showed up.
Mm-hmm.
In the higher rank one, is it abelian connections or is it like reducible connections?
I think it's abelian, but I would have to check. There is more to this. So in what I was saying now, I was saying consider strictly connected tree-like graphs, no loops, which means something for the homologic groups, like their dimensions. If you do include the loops, so you're changing the type of tree manifold being considered, then this expression for the homological blocks will change. And the paper where this is discussed is called Mapping Tori for something, also by Gukov, and I don't remember the other authors. And this came out recently. It was also last autumn sometime. So there, this gets modified. This the type of connections that are labeling these z hat invariants.
Oh, I see. So you're saying then even for the SU2 case, you might have also the non-abelian connections coming up.
I think so, but I don't remember now exactly.
Thanks.
Other questions? Okay, if not, just thanks. Ioana again. And resume in 10 minutes for the last talk of today.
So I hope this was somewhat fun because I was very conflicted about this. It's incredibly fun to work on it, but at the same time, if I was to actually talk about exactly just what I do and the type of tools used, unless someone is really hardcore in